Welcome back. Here we are in part 3 of our lecture. Now remember, way back in the beginning of this lecture, I told you there's going to be 2 important ways to be able to picture pressure. One, we've spent quite a bit of time on already, which is all about the force these little air molecules are exerting as they hit a surface. But there's a whole separate way of thinking about pressure too. That is thinking about pressure as the weight of the air above you. I mean, air, you don't have to think about air having weight, but air has mass, and Earth has gravity. Well, mass and gravity together make weight. So that air that's around you has weight. Which, you know, the idea that pressure should have been related to the weight of the air above you kind of makes sense when you start thinking about the unit pounds per square inch, right? Strictly speaking, pound is a unit of force, but we use it all the time in our daily lives to mean weight. So it's pounds per square inch. How many pounds of air is there above a square inch at the surface of the Earth? Alright. That again is this connection with this prefix bar, like barometer, or the part that is in millibar, or our contours on our weather map of pressure are going to be called isobars. Bar is a prefix or suffix that means something like weight. So these are barometers and so on. This business about pressure being the weight of the air above you is really important because it tells us something about how pressure is going to be changing with respect to height. And that is, pressure will be decreasing with respect to height. Pressure will always decrease with respect to height. And that makes sense, right? The farther up you go in the atmosphere, the less air there is above you. Notice that pressure is the weight of the air above you. It doesn't mean the weight of the air around you. It doesn't have anything to do with the weight of the air below you. It's just the weight of the air above you. So as you go up in the atmosphere, the pressure will always decrease. In fact, it decreases at a really interesting rate. It cuts in half for every 5.6 kilometers you go up. In fact, if you're in the ATSEVS113 lab, you're going to do a lab activity that's about that if you haven't already. But for every 5.6 kilometers up you go, the pressure decreases by a half. So if at the surface at a height of 0, the pressure is 1,000 millibars, go 5.6 kilometers up, and the pressure is half of 1,000 or 500 millibars, go up another 5.6 kilometers and the pressure is 250. Go up another 5.6 kilometers, the pressure is 125 millibars, and you just keep going and going. But there's something interesting here about that. Notice that you never then reach 0 pressure. Turns out that as long as you are in the atmosphere, you just keep going up, the pressure will never quite get all the way down to 0. That's interesting. I also think it's really interesting that it's only the weight of the air above you that matters. But that's actually something you probably could have thought through if you had thought about swimming. When you go swimming, the deeper you swim, the more pressure that's on you, as the weight of the water is crushing in on you. Now, if you dive down into like the 3-foot section with the little kids, there's not that much pressure. You go down into the diving well below the diving boards where the depth might be 12 or 15 feet. It can be pretty uncomfortable. And of course, if you're diving to greater depths than that on like a scuba trip or something like that, it gets greater and greater pressure. All of that is just the weight of the water above you pressing in. The water below you makes no difference whatsoever. If you swim 3 feet below the surface of the swimming pool, you are experiencing the same amount of pressure as you get 3 feet below the surface of, say, the ocean. Never mind the fact that in the ocean the water might be a mile deep below you, and in the swimming pool it might only be a few feet below you. The part below you doesn't make any difference to the pressure. It's only the water above you that matters, between you and the top of the pool, or between you and the top of the ocean. Swimming in deep water is no different than swimming in shallow water. Same exactly way in the atmosphere too. The air below you doesn't make any difference, it's just the air above you. But this connection then between the height and the pressure will turn out to be very, very important in this class. And again, because you have things about that in the homework, and you have things about that in the book, and you have things about that if you're in the ATS114 lab, let's not spend just too much time on that right at this exact moment. We'll come back to that more times in the semester. But in the meantime, let's answer a couple quick questions about this. Question 7. This average sea level pressure on Earth is 1,013 millibars. Now, Death Valley in California is a place, it's the lowest point in North America. It actually sits considerably below sea level, a few dozen feet below sea level. We would expect then that the average pressure at the surface in Death Valley would be A, greater, or B, less than the 1,013 millibars. So if Death Valley sits below sea level and is lower, closer to the center of the Earth than sea level is, how should its pressure be? Should it be higher or lower than 1,013 millibars? Make a choice from those two options and get a little feedback before you move on to question 8.